Hi and welcome back. In this video, we're going to be talking about function transformations, specifically transformations that are either compressions or stretches. So the idea here is that we can take functions and scale them, meaning we change the scale of the function, by either compressing or stretching them, horizontally or vertically. So of course we can actually do both of these. We could compress it horizontally and stretch it vertically, or some combination like this. But the idea is that we can have horizontal or vertical scalings, and they could be either compressions or stretches. So compressions make the graph smaller. I think that they shrink it in some capacity. And stretches will make the graph larger, and they'll expand it in some capacity. So both of these are scalings, if you wanted a bigger word to call them. So scaling, which is basically just changing the scale of the graph. That's why scaling is the word we use. So I want to talk about what these look like as they're applied to both the inputs and the outputs. So there's a little more information in this one, so bear with me as we go through it. Then we will practice it on a graph, and then I'm actually going to do a small example with you too, just to really reiterate the concept. So for the input transformations, these are going to look like f of b times x. So we're affecting the input by multiplying it by b. This is our horizontal scaling. Then we also have a vertical scaling, and here we're going to be multiplying the output by our number, and so we're going to have a times f of x. So for the input transformations, this is a horizontal scaling by a factor of 1 over b. And then for the output transformations, this is a vertical scaling by a factor of a. So you might notice that we're doing 1 over b for the input transformations, which seems odd because we're doing only a for the output transformations. So this is where the input versus output can just feel a little counterintuitive. I again go back to the same explanation I used in the shifting video, which is that the input transformations are happening to the axes. So if the axes are being stretched, then the graph is going to shrink or compress. So that's as much of an explanation as I have for right now. And hopefully as we go through it, you can continue to see why this works the way it does. So now let's talk about how we know if we have a compression or a stretching. So in all of these, we're going to assume that a and b are positive values, because if they were negative, we'd have a reflection. So we did reflections separately. Here we're looking at just positive values. So if b is between 0 and 1, we see that this is a horizontal stretch. So my reasoning here is that if b is some small value between 0 and 1, if we're doing 1 divided by that small value, we're going to get something really big. So the analogy I like to make is that if we have $1 and we need to split it up into pennies, so pennies being very small, so if we were $1 divided by a penny, we're going to have 100 pennies, which is a big value. So even though we just started with $1 and we divided by a penny, we ended up with 100 pennies. So here, if we have 1 and we divide it into a small value, then we're going to get a big value as a result. We're going to get lots of those small pieces. So this is just some number sense to hopefully make you believe me that 1 divided by b, if b is between 0 and 1, is going to be a big number, which corresponds to stretching. So this means the graph is stretching horizontally. Then alternatively, if we have b being greater than 1, then this is a horizontal compression. So the graph is shrinking or compressing horizontally. You can think here, if we have 1 divided by a big number, that's like a fraction, like 1/10, 1/20. It's 1 divided by that big number that's bigger than 1, and so we're going to be compressing the graph. Okay, now to the output transformations. So if we have a being between 0 and 1, this is going to be a vertical compression. That's because we're simply scaling by that number between 0 and 1. So if it's something less than 1, we're going to be compressing the graph. Then if a is greater than 1, this is a stretch. So we're stretching it vertically. As a comment on both of these, if either a or b is just equal to 1, nothing happens. So when it's equal to 1, this is like our static graph because it's just 1 times the function or 1 times the input. And when we do this, nothing changes. So we really care about the times when a or b is not 1, and also if it's not 0. So if it's 0, everything just goes away. So we care about other values that actually affect the graph versus either leaving it alone or just making the graph disappear. All right, so let's look at our example. So I'll do the horizontal scalings first. So here you'll notice if that I'm doing a value that's less than 1, the graph is expanding or stretching horizontally. Then as we get values that are greater than 1, we are doing a compression or a shrinking horizontally. So this is sort of when I'm hoping that see it and believe it will be effective here. So we're saying that if the value is between 0 and 1, it's a stretch, and if it's greater than 1, it's a compression. And hopefully you can see how that happens here. Then for the vertical scaling, when we have a value that's between 0 and 1, we are compressing the graph vertically or shrinking it vertically. And if we have a value greater than 1 for our a, then we do a vertical stretch, so we're stretching out the graph. Of course, we can also do both of these at the same time, so we can have a horizontal and a vertical scaling occur at the same time, and they can either be both compressions, both stretches, or one of each. So we have lots of options here. All right, so just to really reiterate how these work, I want to do 4 quick examples where we write out in words what is happening with a transformation that is a scaling. So we're going to look at f of 3 of x, f of 1/4 x, 2f of x, and 1/2 f of x, and just write out what each of these transformations does in words. So first, with f of 3 of x, I'm noticing that this is a horizontal transformation because it's applied to the x value, which is our input. Then we want to know if this is a compression or a stretch, and what factor is applied. So here, 3 is greater than 1, which puts us in that b is greater than 1 category. This means that we have a compression, and it's happening by a factor of 1 divided by 3. So we do 1 over b, and here b is 3. So this is a compression by a factor of 1/3. This means that all of the input values would be multiplied by 1/3, and those would become the new input values. All right, next we have f of 1/4 x. This is also a horizontal scaling since it's occurring on the inside of the function, which means it's happening to the inputs of the function. So here, 1/4 is less than 1, so we're in that case where the b value is between 0 and 1. This means that we have a stretch for our transformation. Specifically, this is a stretch by a factor of 1 over b, where our b is 1/4. So 1 divided by 1/4 is our factor that we're stretching by, and I like to just simplify this. So we have 1 divided by a fraction, we multiply it by the reciprocal, and so we get 1 times 4 over 1, which is 4. You could also always do this on your calculator. You can do 1 divided by 0.25 or 1 divided by 1/4, and you should get 4. So here, this is a horizontal stretch by a factor of 4. This means that all of the input values will get multiplied by 4, and those will become the new input values. All right, let's do the next 2 examples. So for 2f of x, this is going to be a vertical scaling since it's being applied to the outside or the outputs of the function. I notice here that 2 is greater than 1, so we're in that a is greater than 1 category, meaning we have a stretch by a factor of 2. So the vertical transformations are a little easier to calculate since it's just by a factor of a. This means that all of the outputs of the function are being multiplied by 2. So that's how that stretching is occurring. We're just multiplying all of the outputs by 2. Then lastly, we have 1/2 f of x. This is also a vertical transformation since the 1/2 is being applied to the outside or the outputs of the function. Here we're in the case where we have 1/2 being less than 1, so a is less than 1, which tells us that this is a compression by a factor of 1/2. So this is a vertical compression, and we're taking all of the outputs and multiplying them by 1/2, which effectively compresses the graph vertically. So there we go. That's a little bit of example and introduction into how we do compressions and stretches of graphs as transformations. We'll do more examples in a following video, but that's it for this one. Thanks so much for watching, and I will talk to you in the next one.